There are two different lessons in here looking at volumes. Volumes that it becomes more difficult just because of the visualizing it. Not necessarily the calculus is not any more difficult. It's exactly what you just did. It's just visualizing the shapes, because of the problem of something three-dimensional on two-dimensional paper is difficult, obviously. Well, if you have three-dimensional paper, then, and I don't even have three-dimensional paper here, so you can bring it next time. Anyways, prerequisite thing number one is, guys, prerequisite thing number one is you need to remember what the volume of a cylinder is. Actually, you need to remember what the volume of any kind of shape that is the same cross-section all the way through. A cylinder, if you sliced this cylinder crossways there, every slice would have the same shape, right? If you slice this way, every slice would have the same shape. If this is a cylindrical loaf of bread, I don't know how you'd make that, but if it was a cylindrical loaf of bread, every slice would be exactly the same shape. If you have some shape like that, the volume of the thing is area of the base times whatever this is, right? The volume of some kind of a prism or a cylinder is area of the base times the height, right? We're okay with that? If it's a cylinder, the area of the base is pi r squared, right? So, the specific formula for the volume of a cylinder is pi r squared h, but that would work for anything, right? If you have a rectangular prism here, and it's almost. Let's pretend it is. If you knew the area of the base here or the top, right? Because if you have some three-dimensional object there, if you know the area of the base, you know how many little cubes fit into one layer, right? To go back to first principles, the volume of something is, if you count how many little blocks it is made up of, right? How many little centimeter cubes or something like that, right? When you first learn about volume, that's what you're talking about. If you know the area of the base, you know the volume of one slice of the thing, right? If this is 10 by 10 here, one layer is 100 centimeters cubed, right? The area of the end is 100 centimeters squared. And then if you know this dimension, if you know that this is 13 centimeters, if you know each layer has 100 centimeters cubed in it, and there's 13 layers, it's 1300, right? You multiply that. Oops, got a little crazy with the zeros. Okay, that's the concept of volume. When you first start learning about volume, you're just counting the little blocks, right? Like these happen to have some sitting here, right? This milk carton is 1 liter, 1,000 cubic centimeters. Oh, you think they don't? Yeah, I need a camera here, eh? But as long as you have the concept of volume, we're gonna find the volume of things exactly the same way that you find it in grade 8, or when you first learn about volume, by considering the thing as slices, right? Except that we're going to use calculus then to make the slices really skinny, because we're not going to do things that are the same shape all the way through. In grade 8, everything had to be a consistent shape, right? Like this, if this is the area of the end, no matter where you put it here, it's the same, right? If that circle is there, it's the same circle all the way through. If this, if I could possibly grab this, probably not, but the end's going to go too. But that's the same anywhere you put it, right? That thing? Okay? We are going to do things where it's not the same the whole way. A cone you have from previous grades because it's a nice straight side, but we could do something that is, as long as you have a formula for the side of it. If you have a curve like that, you have some shape that looks like this, I guess. Kind of like, okay? As long as you have a function for the side, then you can come up with it. The way we're going to come up with the volume of this is by considering that you can get this by rotation. Okay, so the first part is things that have a round cross section. They don't have to be cylinders where it's all straight, but they have to have round cross sections. For the first thing we're doing, we're considering getting it by rotating a shape around an axis. You can get a cylinder by, the cylinder is the simplest one you can get. If you consider an axis down the center of this cylinder, and then consider where the radius is, right, there's the center in the middle there. Here's the back part of it. There's a rectangle in here, right? If you take this rectangle and rotate it around this way, okay, around, it's going to sweep out that shape. Okay? This is where we need to spend some time finding good things on the internet to visualize this. That's what I was looking for before. This, if you take this strange shape here and sweep that around the center axis there, so this cross section there, and rotate that around, that's why we're talking about volumes of rotation. All right. So to get that flower, this flower vase here, or whatever it is, if you had a curve that looks something like that, and you looked at this area underneath it here, so if you took this area all the way to there maybe, and there, and you rotated that around, okay, so we start with that, and we're going to take that and rotate the entire thing around. Now you can't show that on here, but we'll look at the things on the internet in a second. This line right here would sweep out kind of the top of the thing, right? It's going to be a circular. You're rotating everything around, right? I can't draw every single point, but around I'm rotating it around the x-axis. Okay. Eventually we'll do it around the other axis because it's then going to be dy, right? We'll start with dx.
What happens if like the base or the boss is like different functions for like lines and lines?
You mean like over here it has this big sticking out part here or something? Then we can't do it with this. Here all we were going to do is things that are circular cross sections. But the step up from grade 8 is they don't all have to be the same size circle, right? In grade 8 it was circle or square or something. And as long as you know the area of that, then you just times it by whatever the height is, right? Yep. It has to be kind of symmetrical around, yeah.
That's exactly what it says, area and times by 50.
Well, what we're going to do is do exactly what we did for 2 dimensions. Okay, hold on. For 2 dimensions, if we wanted the area from there to there, if we wanted this area in here, then what you did is you said we're gonna divide it into rectangles, right? And we're going to say this is dx, delta x, right? It's the width of the rectangle times the height of the rectangle, f of x, right? That times that. And then we just did the sum of all of these, right? And they were different sizes, but we did the sum of all of those from a to b, right? That's where this integral from a to b of f of x dx came from. We're summing up, basically you're summing up the heights, right? For infinitely thin rectangles. You're doing the height times the width of the rectangle. For 3 dimensions, what we have to do is, if you consider any one given slice here, like right here, okay, if that's one of the slices, and if you drew it actually as a slice that had some thickness here to it, like this, sort of, okay, it's a, I guess you need the dotted line in behind there, but it's a disc, right? It's like a coin, a circle that has some thickness to it, but not much. The volume of that thing is still the thickness of the slice, which can be delta x, or eventually when you squish it infinitely skinny, it's dx. It's like any cylinder, it's the height of the cylinder times the area of the circle, right? The area of the circle. The area of the circle is all of this stuff in here, right? The area of the circle. Area of circle. Times the thickness, right? Thickness. In words, we're looking at that first, right? Thickness times area of circle. So what we're doing here for volume is we need the area of one slice, or sorry, the volume of one slice. Volume of a slice is the area of the slice, the area of the side, the cross-sectional area, times delta x, or in other words, area of x, except that looks like a triangle, area of x dx. And we are going to do the integral because the volume's the sum of all of the individual volumes, right? Just the same way you did the sum of all these things. I have to stop here anyways. This will have to be continued in the next one.